Okay, so who has started working on their project? That is not enough, guys. What is the rest of you? What are design project? I am very sympathetic, but it is what it is, right? Make sure to start working on this project as soon as possible. The reason is I won't be able to extend the deadline. There's no way I can extend the deadline because the deadline is on the final exam time for this class, meaning that this is the last time I can give you any assessment, right? Or I can let you submit any like project or whatnot. Right? So you have to start working on it as soon as possible. I have uploaded last year's recording of the project demos on Blackboard, and we are going to spend this 2 lectures, last 2 lectures on like helping you guys. We can also, if you need, I guess, more help, you are welcome to come by my office, or we can meet over Teams, or if all of you need help at the same time, we can reserve a room and just have a classroom setting class session. Does that make sense? Okay, so this is what we're going to do. I'm going to talk a little bit about these parts of the projects, about the background physics and mathematics, just a little bit, and then we're going to move on to actually making the geometry and running the simulation. So I think that today we are going to be able to cover at least the first part, which is the ramjet part, and then on Wednesday we'll be able to finish it by covering the rocket and the resistor jets. And then the thing is, if you can get the ramjet to work, the other parts are not going to be that difficult to master. And you have to keep in mind that these demos that I give suggest all of the dimensions, all of the numbers that I put in are just made up, right? These are real numbers. I don't really expect you to use real numbers, but these have to be whatever dimensions, like mass rates, whatever you use, have to be informed guesses if they are guesses. So I definitely need some sort of a reference, and a reference can be a reference to an example or a problem in the book. That is also an acceptable reference, right? But you have to provide some sort of a reference for the numbers you're using. And by numbers, I'm referring to the dimensions of the rocket, resistor jet, and the ramjet or a scramjet, and also mass flow rates, like all of the design parameters. Okay. Okay. So who is in lab 2? Half of the class is lab 2. But you also have an area, like those of you who are not in lab 2, I assume are in aerodynamics, right? Yes, 265. Who is in 265? And here in 265, you guys have a Fluent-based project. So you're already familiar with computation. Who is not familiar with, I guess the correct question to ask is this: who is not familiar with computational modeling whatsoever? Okay, that's good. So you don't really have to start from the very basic. The idea here is that we have to create a geometry for the ramjet. This is going to be very simple geometry, symmetric geometry. If you guys will essentially 2-dimensional, it can be axisymmetric or planar symmetric. And we just run a 2-dimensional simulation analysis on that geometry and answer a couple of questions. There are a couple of things you need to know when you are designing the geometry for the ramjet. You don't have a chalk. Sorry. So we can talk about it on here. Let's begin. So we are only going to use the fluid flow module in Fluent. You can just drag and drop this anywhere. These three are the ones that I just made before class. It's some sort of a practice for myself. It gives you all of the steps you need. We can use the CAD software that are given, that are built in ANSYS to build our geometry. Then we have to mesh it, set it up using the Fluent software, and do the analysis, right? There are three different CAD software included in ANSYS package. One is called Discovery, one is called Space Claim, and the oldest one is called the Design Modeler. I always use the Design Modeler because this is a software I have been using for the past 10 years, I think. But you are welcome to use the other two software, or you are welcome to use SolidWorks and CATIA, whatever software you use for CAD modeling. It is better to use the built-in software, mainly because the geometry we are creating is a very simple geometry. It's just a couple of lines and a surface, right? Okay, so when you open the design model, this is what you're going to see. We are going to go to this sketching part right here to create a sketch of our ramjet, first of all. Okay. I'm just going to create it using lines. And you have the scale here. Where is the mouse? Why don't I see the mouse? You have the scale right here. This says this line in this geometry is 20 meters, which is an appropriate scale for ramjet modeling, but it is not an appropriate scale for resistor. It's much smaller. So you want your scale for resistor jet to be in like 1 meter to 2 meter range. Okay. Let me, for whatever reason, yeah. Let's make it a question. Those of you who have been in lab 2 or on lab 2 right now, or on aerodynamics, what is my first step in building a geometry for fluid flow analysis? What should I build? Like when you're building a geometry for a stress analysis, just sketch the geometry. That's it. Do you have to do anything else? Yes. Control volume. We have to make a control volume, essentially. Why do we have to make a control volume that surrounds your geometry? Is because we are simulating that control volume with fluid flow. We don't really care about the structure. We care about the movement of fluid around your geometry, whatever that geometry is, right? In here, in this case, the geometry is a ramjet. We don't really care about the stresses that are exerted by the geometry. We do care about the reasons for those stresses, which is the movement of air. So I'm going to create the 40 meter by 40 meter geometry, or around. I'm not really measuring these lines. I'm just drawing them. Whenever you see this P in design model, it means that you are on the point. So you are starting the line from a point. This is what we want to do. We want to make a closed sketch. So later on, we can turn it to a surface. Okay? And whenever you see this H, means that your line is a horizontal line. Does it have to be a horizontal line? Not really, not for the control volume, but it will be easier for the solver to deal with a horizontal boundary. And again, I want to be on the P, and so I have three sides of my control volume. This line here will be my symmetry line, right? You can do a completely two-dimensional geometry as well, but if you can cut your geometry in half, you should, because you will reduce the computational expense by half, right? Even half the computational expense, amount of resources you need to run a simulation. Okay, so let's draw the ramjet. Ramjet has a couple of different parts. The first one is an inlet, which usually looks like this, something like this. It usually starts with a nozzle, and then we have a moving part in the middle, like this. So this is a moving part Delete this line. Again, all of the dimensions I'm using here are just arbitrary dimensions. It is all right if you use arbitrary dimensions, but they have to be informed arbitrary dimensions. Right? You have to make sure you have a reference that tells you where the dimension is. Okay. So, and the flame the flame inlet should be somewhere here inside the ramjet. This is essentially where the air is compressed by the shock waves. And what I do usually is I just assign the flame inlet as a very small part of my geometry of the body of the ramjet. You don't have to do this. You don't have to follow this, but again, I just do this for the sake of simplicity. So this is my fuel inlet, and the rest of them are lines. And then you get to your convergent divergent nozzle. Not the best design, but I think it will do the job fine. And then you have to make sure that you are in a closed surface. So we have created half of the ramp. This is your convergent divergent nozzle. Your fuel inlet. This is your inlet, geometry inlet. Again, ramjets do resemble something like this, but will not look like this at all. They are a little more complicated, right? And we are keeping it very simple for this demo because we want to finish it at some point. Do we have any questions about the geometry building? Yeah. So what you do next is you don't really have to generate this, but you generate the sketch by pressing this generate button. You go back to the modeling, you go to concepts. We are planning to create a surface from sketches right here. That's it. This is your geometry. Okay. There are a couple of things you definitely need to know about this geometry. You need to know where this inlet is and what the size of it is, because later on we have to create a line here and also at the exhaust, because we have to measure the mass flow rate that's passing through the inlet and the exhaust. Why? Why do we need to measure the mass flow rate and velocity at the inlet and the exhaust?
The mass flow rate just allows you to confirm that the model's working because it should be equal. Oh, plus.
We have the ratio for that, for the conservation. Continue. Yes.
For the fuel and air ratio.
That is sure. We can that, yeah, but that's not the main purpose. But yes,
Calculate the first.
calculate the thrust. Your eventual goal here is to calculate the thrust and all of the other performance parameters that depend on thrust, right? And to calculate the thrust, you have to have an inlet mass flow rate and an exhaust mass flow rate, and the velocities, right? And you have to also keep in mind that the velocity is going to change on the inlet, so you have to find an average of the velocity at the exhaust and the inlet. Okay. So let's move on to the next parts. You can just close the software. So you can see there's a check mark in front of my geometry, meaning that my geometry is complete. The next step for us is to create a mesh. What is a mesh? Who can tell me what a mesh is?
You just are essentially discretizing like indefinite domains. You can just solve the continuity equations within individual squares. It's a bad explanation, but yeah.
Discretization is usually used for the equations, not the charge. So the assumption we make while using this method of analysis, specifically finite volume method, not finite element method, finite volume. We don't use this finite volume. It's a mathematical method. Same working principle, just a little different mathematics. Okay, is that the changes are linear. So we can discretize our huge partial differential equations and treat them as linear equations. The changes inside this geometry have to be linear, right? But we already know that the changes are not linear. We have sharp face here, right? This is definitely not linear. So what we do is we break down the geometry into smaller cells, right? And the cells have to be small enough so that the assumption of linearity makes sense, right? And then these cells talk to each other. So the exit of a cell is the inlet of the next cell, and so on and so forth, right? This is what a mesh is. You just break your geometry down to a smaller elements, smaller cells. Like in finite element, we call these elements. Like in finite volume, we call them cells. Okay, so this is the meshing software. There are a couple of things we need to do here. We need to assign names to all of the boundaries of the geometry. What are the boundaries? These are these edges, right? There, these lines, and you see them everywhere. And we also have to break this geometry to a smaller cells, which is done through this module, mesh. When you click on this, you see it gives you a couple of options. The first thing it asks you is what is the physics that you are trying to solve. If our physics is a fluid physics, so we are trying to do a computational fluid dynamics analysis, CFD, right? We can also change this to mechanical, nonlinear mechanical, electromagnetics, like different types of solvers, which are all of the scope of this course, right? And then we have different fluid solvers within the ANSYS package. The most common one, the most famous one for general fluid flow analysis is called Fluent. All of these used to be separate softwares. ANSYS ended up buying all of them and actually put in the same package, in the workbench package, right? So the software we are using is Fluent, and then the next thing you're assigning here is the element size, the biggest element size. It defaults for this specific geometry, it has defaulted to 2.5 meters. Is this a small enough element size? No, 2.5 meters is very big for a 40 meter by 40 meter geometry, right? So we want to make this smaller. I'm going to set it to 25 centimeters. So the biggest element you're going to see in this mesh is going to be 25 centimeters by 25 centimeters. That's the idea. But that is also not small enough for an actual ramjet simulation. It has to be much, much smaller because we have shock waves present, right? Shock waves are very, very narrow, sharp changes in the geometry. Okay, and then you can do more with the sizing, quality of the mesh. You can change how the mesh is inflated, how the mesh grows as you're building the mesh. You can also add a lot of options here. If you right click on this, you see it says in the insert menu, you have a lot of options. You can change the meshing method. What does this meshing method says? It talks about how you are going to divide up this geometry. We can divide it up into small rectangles or small triangles or small hexagons. A lot of different methods. For a geometry, I'm going to actually select this. For a geometry that is like this, which means that it is not a very straightforward geometry. There are a lot of sharp edges. It is usually better to use a triangular mesh, meaning your cells are going to be triangles, not rectangles or squares, right? But again, there are a lot of other options. You can actually do sizing, which will let you choose the number of points you are going to have at different parts of the mesh. That would be the most appropriate way of meshing this type of geometry, because most of the things happen here, right? The rest of the contour volume, nothing really happens, right? We can have bigger mesh here and a smaller mesh here. But again, we want to keep it simple. So we'll just use a uniform mesh. And you can generate, will create the mesh for you. You see, our geometry is divided to small, very small cells. See? So essentially, our equations are going to be applied to these small triangles, and we are going to solve our equations for each triangle. Then we're going to see how much the flux of each variable is out of the boundaries of a triangle. Like how much is the momentum flux, how much is the mass flux, all of these things. And then we relate each triangle to each other, give you a final solution. Okay. Meshing is done. Do you have any questions here? No. Next step is to name all the boundaries. I want to change this selector to edge selector, because we are going to name the edges here. This one is called an inlet, because it is going to be an inlet. This will be the top outlet. This will be the back outlet. And this will be the symmetry line. These are all walls except for the fluid inlet. And this is the fuel inlet. New menu appear here, new whatever you want to call it appear here, and we have all of the selections right here. Do you have any questions? So everything's crystal clear up to this point. Sounds good. You see this, this is a thunder, right? Sign. Means that your mesh is not updated. For whatever reason, the Fluent software and the meshing software in ANSYS don't really communicate with each other very well. So whenever you're done with meshing, you have to right click on this and hit updates until you see the check mark. And then we can open the setup, which is your Fluent software. With the student version, you can, this is the number of processors you can use. Of course, if you increase the number of processors you're using, it's going to go faster, right? Student software, which I have installed on my own computer, is limited to maximum of 4 processors and maximum of 1 million cells. I don't think you will ever reach that 1 million cell maximum for this project at least. But the number of processors you have to make sure that it is 4. But if you use the Fluent software that is installed on the lab computers, all of the computer lab have ANSYS installed. I'm talking about the computer labs upstairs. I've also asked IT to install the ANSYS in the computers that are in the Aero lab, so they should also have ANSYS. But sometimes they have problems. I don't really know why. Yeah. So on those computers, you don't have these limitations, not the cell limitations, and also not the number of processors limitations. This is Fluent. You will be working with this menu right here, but these two menus are essentially the same. The menu on top and the menu on the left are very similar. They give you the same options. Menu on the top is a little more comprehensive. Again, we are not using this. So let's go through each tab separately. And will stop whenever needed. When you double click on a tab, it will give you the options that are available, right? But double click on the general tab, it has three different sections or two different sections: mesh, solver, and I guess another section, gravity. Mesh, in the mesh section, you have a couple of options that will let you determine the quality of the mesh, right? Do we need to run this for this project? Not really, because your geometry is a very simple geometry. So you will probably have a fine mesh. You don't really need to evaluate the quality of the mesh. The other part is the solver part. And we have different types of solver: pressure-based, density-based. Who can tell me what's the difference between a pressure-based solver and a density-based solver? Those of you who have started working on this project, I'm sure, I assume you have watched the tutorial, old tutorial posted, right? Yes.
In the tutorial for the demo from last year, you just said that software works better with pressure, the solver.
Okay, I didn't really explain it last.
Yeah.
Okay. Thank you. That is, that used to be true, not anymore. So both of them can be used for incompressible, the density based, most of them can be used for incompressible and compressible, but the difference is one assumes in the Navier-Stokes equation, the momentum continuity and the energy. One of them assumes density is constant, and the other one doesn't make that assumption, right? Do we have to make a variable density assumption for a compressible physics in the Navier-Stokes equations? The answer is no. There are other approximations we can make, and we are going to make use those approximations to make an incompressible Navier-Stokes, to change an incompressible Navier-Stokes to a compressible Navier-Stokes. But it is easier for us to deal with the pressure base. It's a little fewer hassles. Right? Velocity formulation, we are going to keep it as absolute because we don't really care where the origin of the frame of reference is. But there's another dynamics simulation, so keep it as absolute. And then this is a steady case. We don't really care about the changes of things over time. We just care about one snapshot, right? So we want to calculate the trough for a specific velocity and not the other performance parameters. And the other thing is talking about whether your simulation is planar or axisymmetric. If you treat it as planar, which is what we are going to do right now, it will just copy whatever you have on top to the bottom, right? So it will be a two-dimensional case still, but there will be a symmetric plane right here. If you treat it as axisymmetric, it will rotate your geometry around the symmetry axis, making it a three-dimensional geometry, right? Essentially. Is that beneficial to our simulations? Not really. Because if you rotate this whole thing, instead of one fuel inlet, you are going to have a fuel inlet line, right? That is not a real case. So using an axisymmetric solver is not necessarily beneficial for this simulation. A real three-dimensional solver is of course beneficial, but that will be a little more difficult to handle. Okay, so next part I would say is the most important part of Fluent in general. And these are different types of physics you can add or remove from your simulation models, right? So first one is multi-phase physics. What is multi-phase physics? Multi-phase flow in general.
When you have like liquid and gas at the same.
When you have different liquids or liquids and gas, right? So different types of phases and materials, right? Is this a multi-phase simulation?
Yeah, you have fuel.
We have fuel and oxidizer, but we don't really care about how the particles of fuel move in our system. So this is not a multi-phase simulation, right? So how do we deal with the two phases? We treat it as a mixture. That's it. So that's just one phase. The next option here is energy, which when you turn this on, it will solve the energy equation in addition to mass conservation and the momentum equation. Do we need to solve the energy equation? Why? We have combustion, right? And it is a compressible flow, right? When you're solving compressible flow, you are probably using some sort of a state relationship, either gas law specifically, right? That relate pressure to temperature, right? So we have to solve for temperature, energy equation. You want to make sure you do solve the energy equation. And then the other one is the viscous model we are using, right? Essentially, you are changing how you treat viscosity. We can neglect the viscosity, right? And solve an inviscid flow. Or we can bring in the effects of viscosity, which also means we have to see whether the flow is laminar or turbulent, right? Whenever you bring in the effects of viscosity, your flow can go from laminar to turbulent. Do we know what a laminar flow is, a turbulent flow is? Inviscid and viscous flows? Yes? Okay. So can we neglect the effects of viscosity? No. Why not?
It's a fan flow and acting on your
So the friction with the surfaces is important, okay? And you also have shock formation, right? Which you won't be able to capture with neglecting the viscosity, okay? So we need to have a viscous model. But is this model turbulent or laminar? What is the difference between turbulent model and a laminar model? Or how can we distinguish between these two type of flows?
You distinguish
By calculating the Reynolds number, right? So, do you think this is laminar or turbulent?
the turbulent.
I mean, most definitely it's a turbulent case, right? Why? The Reynolds number depends on your velocity, and velocity here is in supersonic regions, right? So definitely, not only is turbulent, compressible supersonic, actually. So, when you double click on this viscous, what's going to happen is it will give you a lot of options, right? One is inviscid, which neglects the effects of viscosity. One is laminar, and the others are all different turbulent models. Who can tell me the difference between these models for a bonus point, for 2 bonus points, actually? Why instead of having one turbulent model, why do we have different turbulent models?
All of the models just impose different assumptions or approximations.
That is not an answer. No, I'm looking for a better description of what these models actually are, right? Or why do we need to have a different setup, have a different solve from laminar, when we move from laminar to turbulent? Yes.
I'm not really sure, so I thought like there's gonna be different equations, I guess each one solving for.
Okay, that's a little more narrower. Can you elaborate a little more? Do you want to take another shot at it, Matthew? Matthew? 2 bonus points up for grabs. And it's not limited to one person, yes.
Would it be, they're different because you have the more modeling separation?
Okay. And you have studied a little bit on it.
Yeah.
But that is not the whole picture. It is worthy of a bonus, you're asking. So you will get a bonus. Make sure it's 2 bonus. Who else wants to jump in? So, first answer is Navier-Stokes equations are enough for a turbulent model. We don't really need to add anything to our equations. There's the 3 continuity, or not, here is not continuity, or conservation of mass, momentum and energy equation, as well as the ideal gas law should be enough for a turbulent model. But we don't have a closed solution to Navier-Stokes. So we always make assumptions when we are solving Navier-Stokes. So with our knowledge of Navier-Stokes, we need to, I guess, add things to our system, right? If you look here, in front of all of these models, it says one equation, two equation, three equation, and so on and so forth. This means that in addition to the three main equations, I'm solving one extra partial differential equation for a variable that I have defined. This is not a physical variable. It doesn't really exist in real world. This is something I've defined to make things easier for myself. So, like these two models, K omega and K epsilon, are the most I guess famous trivial models. K omega solved an extra partial differential equation for the turbulent kinetic energy K and rotation in the system, vorticity of the system, omega, right? Are these real things that are happening? No. These are parameters that we have defined and we are solving to help the solutions of Navier-Stokes. Does this make sense? Okay, so you need to know more than this about these models? No. You need to make an informed decision on which model to use? No. You can just go by the default one. If the default one doesn't work, just play with the models to see which one works better for you. Is it good to learn what these models are? Of course. But I don't think a lot of you will actually want to learn these models outside of this project. Okay, so I guess the three of you who jumped in will get the bonus point. Just send me an email, get 2 extra bonus points. And then we can add radiation. We don't really have radiation here. I guess a more appropriate version of our project needs to include radiation, solar radiation as well. But we don't. We don't have a heat exchanger, but we do have a species transport. Where do we have a species transport? Combustion, right? And combustion doesn't happen at the injector, but it happens because we are injecting fuel here. Right, there are different models. We don't really need to use a combustion model. We can just use a regular species transport model. And then you want to make sure to tell the software that my reactions are happening not at the injector, not at any boundary, they're happening over the volume of the ramjet, so in the combustion chamber. So you have to make sure you check this volumetric here as well. And then here is where you assign your actual fuel. I'm going to do air and hydrogen. This is asking me what your mixture is. And if my fuel is hydrogen, my oxidizer is always air. So my mixture is air and hydrogen. You don't really need to, yes.
So one time.
Yeah, that happens. You have to find the appropriate folder that has all of these reactions in it. And then make sure that this actually sees that folder. This adds has to be the correct adds. That is a common bug that happens with the software. Just have to make sure that this is pointing to the correct address for this data facility. This is thermo.db, thermo.database. Okay. I guess we didn't really. It did turn on the energy equation by default. And this is model. Do we have any questions about the models? Yes. What is it? Yes, yes. You can change the type of turbulence chemistry interaction that you want to have. Here I've chosen a finite rate, meaning that no interactions between turbulence and combustion, so turbulence is not enhancing the combustion. But we can, I guess, we can choose eddy dissipation. All of these will be done automatically. We don't really need to, you just have to choose an appropriate model. This will be easier for the solver to handle, so let's just stick to 500. But since we have turbulence, we have to make sure we actually have a turbulence model here, which is eddy dissipation, to get the best results. Thank you for the question. Okay, next step is materials. So if you double click on the materials, it will give you all of the materials here. We have the mixture. Let's actually click on the mixture. You can check the reaction, right here. It says reaction right here. You can click on edit. It will show you we are only solving one reaction. Is this true for combustion is happening? Do we only have one reaction? See what the reaction is. It says H2 is my hydrogen. The stoichiometric coefficient is 1. O2, stoichiometric coefficient is half. And then the product is going to be 1 H2O, 1 water, right? That is my reaction. Do we have any more reactions in real world scenario? Yes, the answer is yes. We actually have many more reactions, right? But for the purposes of this project, we are going to keep it to this one because it is not a combustion source, right? I don't think Dr. Wan gives any projects for the combustion course, actually. So, yes.
So out of curiosity, does ANSYS just like assume
It can do chemical kinetics, yeah. No, it has a different, you can actually, there are a lot of options. You can actually import chemistry from ChemChem as well. Have you worked with ChemChem? Yeah. And the one thing that you have to make sure you do change here is density. Density, we cannot assign a constant value to density. Why not? It is going to change with respect to heat, and we are in a supersonic regime. A supersonic regime cannot have a constant density. It's a compressible fluid flow, right? When you're dealing with compressible fluid flow, you're dealing with variable density, right? Does that make sense? Okay, so we did change this for the mixture, but we also have a fluid here. We have to make sure that we change everything. We change the density for the fluid as well. Do we need to change the specific heat, conductivity, viscosity, and all of the other ones? I mean, in reality, yes. But to keep things simple, we're just going to assume that these are constant for the purposes of this project. Questions? Yes, right here. Okay, and you come here. We don't really have a motion of the boundary, so that doesn't really apply. This menu, the other one is cell zone conditions. This essentially tells us what type of material we have in our control volume, which is a fluid, air specifically, which is the material we want to have. I guess it says it's just using the mixture. But we can choose air or mixture. Most of them should be fine. Because the amount of fuel we have in the system is negligible in general. Next one is the boundary conditions. When you double click on the boundary condition, this menu opens. So you actually have to go through all of your geometries, all of your boundaries, all of the edges, and assign a condition to them. You have to tell the software, this is an inlet, this is an outlet, this is a wall, right? And you have to specify a velocity for your inlet. But you have to tell the software that this is my flight velocity. This is the flight velocity at which I want to calculate thrust, right? essentially you're calculating thrust, you need to maintain this flight velocity that you are assigning. Okay? Does this make sense? Okay, so the back outlet, this one, is said to be a pressure outlet, which is one of the types of the outlets. Do we need to know what all of these types of the boundaries are? It is not a bad idea for you to actually at least go through them and see what the options are, but you don't really need to know what all of them are. We are not going to use a pressure outlet. Why? Because when you have two outlets that are perpendicular to each other, you will get a lot of errors at this point where they actually meet, right? So we are going to use another type of, I guess, inlet to represent our outlet. What is the difference between an inlet and an outlet? Think about it. What is the main difference between an inlet and an outlet? The direction of the flow. So if we actually can assign and can use an inlet boundary condition for an outlet, the only thing we really need to do is to have to make sure that we have the correct direction for the velocity, for the movement of air, right? We just have to make sure it is moving out of our system. So one of the inlets we can use as an outlet is called the pressure far field. If you choose this, it will ask you a couple of options. The first thing is it will ask you what is the gauge pressure of that specific boundary. We are looking at this boundary. What is the gauge pressure of this boundary? Who can tell me what the gauge pressure of the boundary? First of all, what is a gauge pressure in general? Yes. Exactly. So essentially, it's a pressure of the gauge, right? What's the difference between the gauge pressure and the absolute pressure? So yes, yeah, it's a total pressure you have measured. Exactly. So gauge pressure is the absolute pressure minus the atmospheric pressure, right? So whenever you see a zero gauge pressure, it means that you are at the atmospheric conditions, right? On Earth, means that your pressure is 1 atmosphere. Is this a true assumption for our outlets? Yeah.
If it's sufficiently big to go by, yes.
Okay.
If it's far from, it should be. So,
If it's a far field, it should be zero. But the value of the pressure depends on your elevation, right? Your altitude, right? Okay. So considering that, is this a true assumption for the pressure of this boundary?
yeah,
So it still is.
That is that the question we should be asking? Do we need to know the elevation?
So the gauge pressure would just be like whatever ambient is, it would change with respect. Like zero gauge pressure at any altitude is the same as saying like the pressure of the.
You just have to go and find the absolute pressure, atmospheric pressure at that altitude, right? Your gauge is always comparing your atmospheric pressure, your pressure with the atmospheric pressure at that altitude, right? So that this can stay at zero, right? Always at all altitudes. What about the atmospheric pressure? Do we have to change that?
That would change with respect to altitude.
And we'll definitely change with respect to altitude, yes. But do we need to change it? Do we need to go to, we are going to see there is a reference values in which we can assign a atmospheric pressure. Do we need to go and change it from 1 atmosphere to whatever altitude we are flying at?
It depends on if you're trying to test like uninstalled thrust or installed thrust. Like you can, yeah.
What else? We are doing installed thrust, right? I mean, technically we have some structure, but not all of the structure exists. So we are doing half installed thrust. Does this mean you have to change the atmospheric pressure?
If you want to know the thrust at sea level, set it to sea level. I imagine you just set it to whatever altitude you want to know the thrust at.
Okay, what else? Who else wants to jump in?
You said it, I guess you need to set it to the test it out.
We do not need to change the atmospheric pressure because in fluid analysis, we only care about the pressure difference. The value of pressure is somewhat arbitrary. The value of pressure only becomes important when you're dealing with the composition of the gases, right? You're not dealing with the composition, like you're not dealing with particle analysis. We don't really care about the particles hitting each other, right? So, no, the answer is we do not need to change this. And the other thing we have to set is the velocity at the outlets. I want to solve this for a Mach number of 2, right? So this has to change to 2. And then you have to assign a direction to the flow. Right now, it defaults to 1 for the x component of the flow direction, meaning that all of the flow is going out in the x direction. And since this says positive 1, means that we are going out, like it is correct, it is an outlet, right? For this boundary, the positive 1 meaning that we are moving in this direction, we are moving out of the system. Okay. Let's do the same thing for the other outlet on the top. What should we do with the species? Set anything for the species here. What is it? No, so the boundaries you are assigning. This is where the solution starts based on your assignment to the boundaries. If you assign it to Mach number of 2, solution will start from the boundary at the Mach number of 2, and then it will solve the rest of the geometry. The answer is yes, we have to change this, right? But it doesn't have to be accurate. It doesn't have to be an exact number. So what do you think we have like in the species? This is for the reactions kinetic. We have H2 hydrogen, we have O2 oxygen, and we have H2O water. Which one of these are going to pass through the outlets?
Far field is going to be affected.
Like far field effectively, that's the definition of far field, right? It will effectively be only air, right? And which means that out of these three, we will only have oxygen. How much oxygen? How much of the flow is going to be oxygen? 21%, right? So the fraction, mass fraction here should be 0.21. Do we care that these do not add up to 1? No, because the rest of it is nitrogen that does not play a role in our reaction, right? So we don't really care about it. We also have to make sure that this is set in the other outlets. And then fuel inlet. For the inlets, we have the option to set the velocity of the inlet or the mass flow rate of the inlets, right? Which one do we have to choose? Which one do you think is going to be working better for us? Mass flow rate is a more common way to think about M.F. is literally mass flow rate of field, right? But what if you want to do velocity? You just have to make sure to convert the mass flow rate to velocity. How do we convert mass flow rate to velocity? What is the relationship between mass flow rate and velocity?
Volumetric flow rate density.
So density multiplied by area, cross-sectional area, multiplied by velocity is mass flow rate. You have to make sure you have the density here, and area of this inlet here, to change the mass flow rate to velocity. If there's in the drop-down menu, there is a mass flow inlet right here. And it will ask you how much of a flow rate you have, I'm just going to say 1 kilograms per second, right? Again, the numbers you use cannot be just random numbers, right? You can refer to an example problem in the book, which is again might be a random number, but that is an informed random number, close to reality. Okay, and then for the inlet that is right here, we can do a velocity inlet. We can still do a pressure far field, right? Because that was an inlet, right? That we use as an outlet, right? Or we can do mass flow inlet. We don't want to do mass flow inlet because you don't really know how much mass is flowing in to the control volume. We might only have control over the mass flow to the ramjet, and that is what we care about. We don't really care about how much mass is coming into the whole control volume. Most of it is going out untouched, actually. So let's just stick to velocity inlet here. And what should be the velocity and what the direction of the velocity should be here. Mach 2. But we don't have Mach number here. We have velocity. See? Who said Mach 2? Yes. Yeah. So what is the Mach 2 velocity? We are all of our other parameters is at sea level. Atmospheric conditions at sea level, density at sea level, all of the reference values for this solution is at sea level, right? Which means that we can calculate the velocity at the inlet for the sea level as well. So what is the speed of sound at the sea level? It's 330 meters per second. So what is Mach 2? 660 meters per second. And then for the direction of the velocity, it says right now in the option we have magnitude, so we have to assign the magnitude, which is 60 meters per second, and it has to be normal to the boundary, which is the correct direction. Or you can change this to magnitude and direction. So in case you want to actually have a different direction of the inlet, for example, if you are doing an aerodynamic analysis and changing the angle of attack, right, you have to change the direction of the inlet, right, not the direction of the actual airfoil that you're analyzing. We can use this. Like x component of the flow is 1, meaning that it is moving in this direction. Okay. Apply and done. So, and for the interior surface body is just the interior of your control volume. We don't really need to do anything about it. The symmetry, because we have named it correctly, Fluent was able to assign a correct boundary condition to it, so we don't really need to change anything here. We have already played with the top outlet, and the wall is also considered a wall. The only things you can actually change in the wall is the temperature of it. We don't really have any heater here, so we don't really need to change anything here. But in case of a resistor jet, we are going to have walls that are going to act as heaters, right? Okay. And then we are not playing with the mesh or we don't really have auxiliary geometries. We don't really need to care about these three menus. This one is a reference value. If you are calculating the lift coefficient and the drag coefficient, the values here will be used for those calculations, like the area and density. All of these values here will be used for those calculations. We are not calculating the lift and drag coefficient, so that doesn't really matter to us. I mean, it might matter for the no, it doesn't matter for the truss as well. We don't really need to do any reference price. We are not creating a new parameter that doesn't already exist here. Then we get to solutions. These methods are the discretization methods that Matthew mentioned. So what are discretization methods? Yeah, we essentially take a very complicated partial differential equation and break it down to a simpler linear equation for the final volume. Those of you who are in finite element method, I'm sure you have talked about this. And you find, no? You haven't talked about this?
I
Oh, you're in.
yes.
Okay. Again, we don't really, if you take a CFD course, I'm sure they're going to talk about it, but we don't really care about it here. But so if you can see, like for density calculation, it's a second order of things. It means that the order of accuracy is a second order. So you're accurate up until 1/100th of your unit. Like the density is one, you are accurate up to 1/100th of kilometers per cubic meter for density calculations. We can increase this to a third order, but the problem with that is it will stiffen your solver, right? And that means that you will probably get, it will be harder for your solver to actually to reach a solution. There is a compromise. The second order should work fine for your project. So you don't really need to change anything here. We don't need to talk about the under relaxation and over relaxations. We need to talk about the report definitions here. Okay. So from this solution, we want to get the mass flow rate and the average velocity here, and the mass. We want to get the mass flow rate and average velocity at the inlet and the outlet. So we have to create a report definition. The new report definition, and these are surface reports. So let's see flow rates right here. It is asking you where do you want me as a solver to calculate the flow rate. See, it's asking you which surface do you want to look at. But none of the surfaces we have already defined are our surface of interest, which essentially means that we have to create a new line, right? Is asking us the dimensions of this line. Right? Where's the starting point, where's the end point? That's why I told you in the beginning when we were building this geometry that you have to know where your inlet is. You have to actually know the exact location of the inlet so you can create these lines, right? I'm just going to create a random line, and it was created as line 7. So I'm reporting the flow rate. We can actually have a mass flow rates. Here we can have another option for velocity. I don't really remember where it was. Volume, average velocity, area weighted. It is somewhere in these menus. Just I will look for it and find it. So as we are solving the problem, it will give us, for the final solution, it will give us the mass flow rate, at a random location. I assigned a random location, but you have to get the mass flow rate at the inlet and the outlet, and also the average velocity, the area weighted average velocity. Do you have any questions so far? How confused are you? Not confused at all. So we have 2 people who are not confused at all. Half of you are already checked out. Those of you who are not checked out, yes. On the inlet right here. Yeah. That's right. And you have to actually multiply it by 2 because it's a symmetrical thing, right? And then in the monitors, yes. Because you're calculating the mass flow that is going to the top side of your ramjet, right? But it's a symmetry. So the symmetry is the rest of the ramjet that is right here at the bottom, right? But we are not solving for it. So whatever mass flow you have here, you have to multiply by 2 to account for all of it going into there. Okay. So in the monitors, you can actually add new windows. You can monitor the velocity. You can monitor the forces. We can monitor whatever you want to monitor. But one thing we will all are going to monitor is the residual. What is the residual? Yes. What does it have to do with there?
It's the difference between the solution and the two iterations.
Exactly. So for these computational, all of the computational models, start from an initial guess, right? And then solve the whole thing again using that initial guess. Compare the final solution to the initial guess. And use the final solution as the initial guess for the second iteration and the third iteration. So the difference between the initial guess and the final solution is called the residual, right? It is not just a simple subtraction because you have like thousands of cells, right? And all of them have their own final solution. But it's just an aggregation on all of these residuals, right? The value you see. So, and this is where you set your own convergence or solution criteria, right? Look at here, continuity. This is for mass conservation. It says the residual is 0.001. What does that mean? It means if the final solution in an iteration minus the initial guess of an iteration is less than 0.001, that is an acceptable solution, right? So you can just say we have reached convergence, right? That is the criteria you need to meet. But those of you who are in orbital, thought and orbital mechanics, that we did talk about the Newton method, right? And we talked about the error. That's essentially exactly the same thing that's happening, right? And your residuals usually start from a higher value, and they go down as you keep solving as you keep like increasing the number of iterations. Okay? Do you have any questions here? Yes. Yes, yes. So your computer will stop computing either by reaching the limit of iterations you have set manually. That doesn't mean you have reached the solution. It just means it has reached the limit of iterations you have set. So you have to run it again, right? Or it will stop when it has reached a solution or it has converged to a solution, or it will stop if it diverges, meaning that the residuals keep increasing and increasing instead of decreasing. As an unstable solver, it will never get to a solution. It will never meet your residual limits. Okay? What time is it? I think we have to stop here. We didn't even get to solve one case. So, but we were close. We are just 1 minute away from this. So let's just finish this. So when you're done with all of the residuals and everything else, you don't really need to make any changes. But the one thing you have to do is initialization, meaning that you have to tell your software what my initial guess is. You have two options for initializations: a standard one in which you actually assign these initial guesses yourself, or you ask the solver to do the job for you. We're going to ask the solver, hybrid initialization, click initialize. It just gave us a warning that we didn't really reach convergence of 1 to the negative 6, 10 to the negative 6. That doesn't really matter, right? We have the convergence values. It is 8 to the negative 6, which is higher than all of our residuals for a solution. You remember the residuals were 0.001. Like 8 to the negative 6 is better than 0.001. So we can accept this initialization. Then you go to run this calculation. We don't care about the pseudo time step setting. The only part we care about is this number of iterations. It has to be larger than 0. I'm going to set it to 10,000 and then hit calculate. See, it is reporting the report definition to me. This is the mass flow rate at that random point, but I can also go to the residuals, right? This is each lines are colored, right? The continuity residual is this one, usually reaches convergence at a slower pace compared to others. You can see the continuity is at 10 to the negative 1, right? the difference between the final solution of an iteration and the initial guess of an iteration is 10 to the negative 1.1, right? Not the best solution, but it is going down a little by little. This is mass conservation. We have x velocity, the white line, y velocity residual. We don't really have any movement in the y direction. That's why the y residual is very low. It's only y direction. You're going to get there.
So you want the lines to, it is more, it's
Go down. And then, you want them to go down as smoothly as possible. If you see a lot of fluctuations, you have done something wrong. I think in the tutorial I posted, we actually get a lot of fluctuations, but we never get to a final solution. Right? We don't get. But it seems like we are getting there. So, and you don't really, you might, yes. It depends. It can be all of them. It can be anything. Yeah. Okay, it is going down a little by little. We are out of time, so I'm just going to stop this. When you have not reached the convergence criteria you have set, that doesn't mean you are not going to have any solutions. But these are solutions that do not meet your expectations of accuracy. Does it make sense? Meaning that right now, we should see some sort of a solution. So we can go to graphics and look at the contours of pressure. And see, so right now I see the low chart that I expected to see. And let's see high pressure regions. Another sharp wave here. I don't really know what's happening in here. But we have expansion waves with expansion fans. But so this is a solution, but it's not the solution I wanted with the accuracy I wanted, right? So if you could never get to a convergence, you can report these type of solutions and mention that we have reached a solution with a residual of 0.1. This is not what I wanted, but this is what I have, right? Does that make sense? So let's stop here. We're gonna come back on